Yeah, I could watch this all night.
You will.
They're off my volume. I think you can still hear my the loop. Soul moving.
Too loud or too soft?
You hear it. It should just be off. You're giving talk.
Robert, would you like to show the pictures, everyone?
Sure. Not best of luck.
This is what is happening now.
Yeah, where's Yoshi? Oh, there he is.
Oh. Okay. Well.
Here. Yeah. So this is, so if you look at a picture of me, you see three solenoids. There's an S in the this is the upstream. This is the upstream part of the S, which was transported from where CDF used to be. There's an assembly hall. So we went at about 2 to 5 miles an hour. Few miles into our hall. And then got moved over, and now it's even lower into its final position.
This is real time, isn't it?
This is your line. This is where our detector is going to be here. It's all right here. So it's going to get back up into this wall.
And then push into it.
Right. So you gotta move it. This is the last film. So the other part of the S will go here. The other part of the S will go here. Production is the piece that comes along here. And the production of the actual. This was going live up here. Wait, because. the other part is also-
W fusion. Yeah, no. So we are thinking of if we are big noise and someone saying, see, that's a bad idea. Right. You have already one. I see. What is the estimation? Yeah, well. Right. So, maybe you die. Of course, yeah. Yeah, that is.
We even had a
Yeah,
blanket.
so.
Yeah, we had a welding blanket, so when you weld, welding gases get out, there's a welding blanket, you couldn't get gases from getting out. But things didn't start, so there was a leak. The welding gas got out and set on fire. Almost hospital showed it. But we were like.
Yeah.
Beautiful.
And yeah, very good. Then you're gonna know big noise.
And that's it. So welcome to the last day of the workshop, and we are super happy to open with talk by Bryman, who will tell us about the Pioneer project that he assigned.
Thank you. So it's been about 40, there were about 40 years separating the discovery of the electron, the muon, and the tau. So I think we're basically a little bit overdue for the number 4, but we can hope. The whole question of lepton flavor universality, conserved lepton numbers, separate lepton numbers were developed in the early middle part of last century by these famous people. And we now know that lepton flavor is not conserved, that neutrinos have small mass and mix, but flavor remains a bit an enigma in our world. There's no real theory to explain why we have 3 generations, not 1, not 10. And we know that there are some famous flavor tensions that we discussed the muon G -2. We don't the controversy about what it means these days. In V decays, there's still the charged current possible anomaly with rather large, or 10% possible deviations. But because of other information, we know that this would have to be involving both quarks and leptons to be consistent with other information that I'll mention. And then there's the CKM unitarity flavor issue, which seems to be mostly due to confusion in the kaon sector through the various measures of VUS or VUS over VUD don't really agree with each other. And this will, whereas in the VUD part, the neutron, if you choose the right neutron experiment and super allowed beta decay, VUD is reasonably consistent. So it's been suggested that the CKM unitarity might be connected to lepton flavor universality, since the extraction of VUD from the super allowed beta decay in particular depends on the Fermi constant coming from muon decay. So you could have modifications to the W lepton neutrino couplings that could influence this. These are all speculations. In fact, when you look at pure lepton universality in mu E universality and tau to mu or tau to E universality, these are extremely well tested at the 10 to the minus 3 level. In mu E universality, as I'll be discussing, the best measure is the pi E nu branching ratio, pi E nu over pi mu nu. But in taus, you have nearly comparable precision, and there's results from kaon physics and even some W decays. So this sector seems to be very well under control, but there could still be hidden gems. And in the case of pi E nu, there's the opportunity to improve the precision by possibly an order of magnitude. And the pi E nu branching ratio, given as the rate for pi to E nu gamma over pi to mu nu gamma, including all the radiative effects, has been calculated over a number of years to extraordinary precision, 0.012%, 10 to the minus 4 precision on the 10 to the minus 4 branching ratio, initially by Marciano and Serlin, and by Trigliano and collaborators. And we say this is possibly the most accurately calculated decay process involving hadrons. The current experimental result is dominated by the pi E nu result from 2015. It's at the 0.19% level. So it's an order of magnitude less precise than the theory, but it does give the best test of lepton flavor universality at the 0.1% level. And there are still data being analyzed by 2 experiments, one from PSI and one from Triumph, aiming to improve this by another factor of 2 roughly. And then the Pioneer experiment, which I'll be talking about, is aiming for another order of magnitude in precision to try and make the experiments of precision comparable to the theory. That's just graphically where it is in for the pi-unit branching ratio compared to the standard model. There's high mass physics potentially accessible if a deviation from universality were observed of order several thousand TeV. So it's in the range of interest or of the lepton flavor violation experiments, and there's a host of potential possible non-standard model physics at high mass scale. Charged Higgs with non-standard coupling, leptoquarks, compositeness, all kinds of things have been explored. And this is mainly for pseudoscalar interactions, but also induced scalar interactions have extreme sensitivity. And when the experiments are done, if lepton flavor universality is observed, you won't know which one of these is involved, and it could actually be an apparent lepton flavor universality violation that you could have other processes happening in which massive sterile neutrinos are involved, or weakly interacting particles like axions, et cetera. And these processes have also been explored, and the experiments are sensitive to them. That's pi-nu currently dominates the low energy mixing for light mass sterile neutrinos. The Pioneer experiment is built on the previous experiment, pi-nu at Triumph and Pan at PSI, and I'll mostly be talking a bit about the pi-nu experiment, which has actually produced a result shown here. And this is what the setup was. A low energy pion beam was brought in and stopped in a scintillator target, and the positrons were measured in a crystal calorimeter, principally the world's largest and best sodium iodide crystal that came from Brookhaven lab, 19 radiation lengths thick, 50 centimeters thick and 50 centimeters in diameter. And one of the interesting things that was discovered in this calorimeter, when an a positron beam was put into the calorimeter directly, into the crystal directly, was we saw a spectrum like this with a series of bumps due to photonuclear interactions when neutrons escape from the calorimeter, and you don't get a smooth peak. You get bumps due to 1 neutron, 2 neutron, 3 neutrons, 4 neutrons, which we all see. And this is a critical aspect of these kinds of experiments, where you need to know the shape of the response function of the calorimeter. Basically, the experiments are simple experiments, just counting positrons from pion decay. So pions are brought into a target, stopped, and you look for them to decay directly to positrons or through the primary decay channel, pi to mu to e, where the muon also stops in the target and has a kinetic energy of 4 MeV. And the energy spectra from the two channels is a peak at 70 MeV with a response function of a calorimeter, and the Michel spectrum, and they have different timing characteristics. The pion decay with a 26 nanosecond time scale, and the pi to mu to e dominated by the muon lifetime. The experiment is the pi-nu experiment, and the same principle is being used in Pioneer, is that many systematic effects cancel when you measure positrons from both channels, rather than trying to get absolute efficiencies for electrons and muons by measuring the ratio pi e over pi mu. But one of the main problems of the experiment is, of course, systematics. And because of the electromagnetic response of a calorimeter, there's a long tail that I showed previously for the direct measurement. And it's below the Michel edge at 52 MeV, one has to make a correction for the remainder of the tail that can't be seen because you have 10 to the 4 times as many pi to mu dE events. So some attempt was made in Pion to suppress the Michel background, and it was suppressed by around 4 orders of magnitude, but still not good enough to be able to actually observe the tail. And so the tail, which is the largest systematic uncertainty, the tail correction for this missing part under the Michel was obtained by the direct measurement of the crystal response and then putting that into Monte Carlo simulation. And the basic technique of the experiment was to divide the energy spectrum into 2 regions, one low energy and high energy. Low energy for pi mu e with this time spectrum, and then the high energy with dominated by the decay, but also with many other little small components at below the 10 to the minus 4 level in the time spectrum, and fits were done, and then the corrections were made for the missing events below the Michel and other corrections. So Pioneer is going to follow the same strategy, but try to do an order of magnitude and precision better than Pioneer has done so far. And also do an order of magnitude better on the searches for sterile neutrinos and exotic muon decays involving multiple neutrino pairs and axions, etc. But in addition, try to improve the precision of pion beta decay. It's presently at the order of 0.6% precision, which makes it sort of irrelevant for the extraction of VUD. But if you were able to get down an order of magnitude in precision, then it would become the cleanest way to obtain the VUD. Those various nuclear corrections wouldn't be, that are needed in the super allowed beta decay wouldn't be necessary. And so in Pioneer, we envision 2 phases of this measurement. One that improves it by a factor of 3, which would help the VUS over VUD issue by being able to compare KE3 with pion beta decay. And that would give comparable precision for VUS over VUD to what is presently available. And then a second phase where we go another factor of 5 to get the full order of magnitude improvement. And this is what the outline of the concept for the experiment is. It was proposed at PSI last year, Paul Scherrer Institute, where mu-3e and mu-e gamma are being done. And it was approved, and we've started to have some beam tests to explore the beam properties and calorimeter properties. And PSI is the ideal place for this. It has the highest intensity beams available. We need a high rate of low energy pions. And so we're going to make incremental improvements over the previous experiments by having a 25 radiation length calorimeter compared to 19 radiation lengths for Pioneer and 12 radiation lengths for PEN. Improve the solid angle acceptance. All of these have major implications for reducing the systematic uncertainties due to the tail correction that I mentioned. And then another major aspect is to have an active tracking target, which also enables us to make a secondary measurement of the tail correction, which I'll talk about in a minute. And then various things. So we're talking about a calorimeter. The initial proposal is to use liquid xenon, as the MEG people do for their electromagnetic calorimeter, surrounding the active target. Between the target and the calorimeter is a tracking detector as well. So these are the main features of the proposed experiment. use the Pi-E5 beam, the same beam that Meg is using now, and have an active segmented target, which is in the jargon is called 5D for 3 spatial resolution parameters, fast timing, and also good energy resolution. And then the liquid scintillating calorimeter, which we envision having 100 picosecond timing resolution and energy resolution as good as 1.5%. The beam is, we've done some beam tests that make things look promising, but there are some challenges. We need to get the beam phase space in better condition and the beam separation, reducing the particle content of the beam. The target is a major element. There are these types of trajectories that we have to look at: direct pi to E in the target, pi to mu to E, decay at rest, and then decays of pions in flight can confuse issues. And then even the decay in flight of the stopped pion, which produces a 4 MeV muon, the muon, which has 2 microsecond lifetime and takes 12 picoseconds to stop, can decay in flight. And this becomes a significant issue for this 12 picosecond time, because it looks very much like a direct pi to E decay. So it creates a background. And this is what the tracking target will be able to do for us in terms of topologies. We'll be able to see everything that's happening and identify these different components. It's envisioned, as I said, to be 5D detector, which is 1D more than is usually considered for collider applications. And the technology that we're investigating is low gain avalanche detectors, LGADs. And there are different species of LGADs that are being looked at. The AC coupled LGAD with a resistive layer is one of the possibilities. It means that there's no dead material between the segments, but it does increase the occupancy. And then there's trench isolated LGADs, which don't have spreading, but have some dead layer between sectors. And then we're also considering a more conventional pin detector, which would have challenges due to long time constants needed to get good signal to noise. These detectors, the LGAD detectors, will do extremely well for 4D, but they were having issues with regard to gain saturation to be able to make a good energy measurement, because we have a dynamic range in the energy that's required of about a factor of 1,000 due to the slow pions depositing a lot of energy in one strip and the minimum ionizing positrons on the way out depositing only a few keV. We're also looking at double-sided silicon strips that would correlate the X and Y components and help resolve ambiguities. There's a tracker between, we'll talk about that. And then the calorimeter that we're mostly focusing on these days is liquid scintillator, liquid xenon. And based on MEG experience, we can expect very good performance. And it has many attractive features. It's bright, it's very fast, factor 10 faster than the sodium iodide that we used in Pion. It's dense and it gives a homogeneous material, but it is potentially very expensive. And preliminary work is done to look at that, and we're building a prototype. We're considering the use of both PMTs and silicon PMs as the readout. As many of you know, there's a silicon PM degradation issue in liquid xenon that MEG has discovered, and it's not a resolved problem. But we're mostly focusing on the use of phototubes, such as the ones that are being used for Panda X that were newly developed by Hamamatsu. This is a picture of the prototype setup that we're developing to try and resolve some of the issues that are still remaining from the MEG experience of using liquid xenon. They only their performance is about a factor of 2 in energy resolution worse than the Monte Carlo simulations. And we want to understand what that is so that we can make good predictions for Pioneer. We're also looking very carefully at a possible lysocalorimeter instead of the liquid xenon. And test beam has just completed at PSI using some new crystals from this Chinese company, Sicus, from Shanghai. They don't tell us what the improvements are that they made to the crystals, but they seem to be better than any lyso crystals that have been produced before. So in the Comet and MUE, some arrays were tested which produced resolution in the 4 to 5% range. And Pioneer wants to have better than 2% resolution. And the tests that we've done at PSI are giving very promising results that make the 2% or better resolution possible with these new crystals. LISO is like liquid xenon, is very bright scintillator. It's as bright as sodium iodide as is liquid xenon, and it's 10 times faster, similar time constant as liquid xenon, but it's a bit easier to handle in terms of segmentation compared to liquid xenon. But in the last few minutes that I have, I just wanted to mention this special Minneapolis diversion we heard about from Matthias and worked by Maxime and company about this possibility of mu to 5e. And we noticed that there was an old experiment done at Berkeley by my Triumph colleagues where they looked for mu to e gamma gamma. They injected a muon beam into a sodium iodide crystal into the center and then looked for the total electromagnetic energy that was produced in muon decay. And this is the spectrum that they got. And so they set a limit of 4 times 10 to the minus 6 on mu to e gamma gamma, which was the best limit at the time, 1974, ancient time. But it actually applies to any total electromagnetic energy that's produced, so it applies to the mu to 5e. And the recently, in consideration of how you might do a better experiment, and I asked Adrian Singer at PSI to calculate what the intrinsic background would be with the McMule formalism, and they basically showed that a similar experiment might be limited at the 10 to the minus 11 or lower level, depending on the energy resolution that can be achieved by the calorimeter. And it turns out that the prototype that we're building for Pioneer would be extremely suitable to this type of measurement. And it looks like we might be able to improve that by 4 or 5 orders of magnitude to the 10 to the minus 10 or lower level in a few days, 10-day run at PSI, which could happen in a year or two. There might occur before mu to 3e, where it was able to go deep into this process. So Pioneer has this issue of finding the tail, just like it is in Pioneer, measuring this small percent, maybe 1% tail under the mu to e. It'll be done but with direct measurements in the current configuration of the Pioneer calorimeter, where we can inject positrons directly. And then it'll also be done by suppressing the background from these processes like pion decay in flight and muon decay in flight. And some promising simulations have indicated that it may be feasible to suppress these backgrounds low enough so that the tail could actually be measured in situ from the data of the experiment. And this is a table of how we envision getting to 10 to the minus 4 precision on the Pioneer, comparing the estimate for Pioneer compared to the current values from Pioneer. And these features that we are improving, the calorimeter and the target, are major components of that. So In 3 years of running, we would collect 2 times 10 to the 8 Pion events, more than an order of magnitude, more than previous experiments. And then the trick will be to reduce the systematic uncertainties to the level, to a comparable level of the statistics. And with pi and beta decay in the second phase and the third phase, we also have less defined plans for exactly how it will be done, but it looks to be feasible. So I'll just conclude and say that pioneers going to join the suite of rare Pion, Muon, and K decay experiments that are delving deep into flavor issues, including lepton flavor violation experiments that we heard about yesterday. And there are new results expected on all of these flavor experiments soon. And we expect and anticipate that Pioneer will be able to make serious contributions to the flavor world through the study of Pion and Pion beta decay. So that's the Pion collaboration.
So do we have any questions?
Maybe an incredibly naive question, but like, could you try to weigh in on MUTE gamma? Because that seems to be your detector is naively set up for that sort of stuff, but I'm sure there are some issues with that.
To do mu gamma instead of
Yeah.
in addition or whatever.
Instead of muted 5 electrons, could you also do muted gamma?
Well, the result would include a limit on mu gamma,
Right.
but it won't be
It will
competitive
not
with
be
neg.
competitive with all, yeah.
It looks like the limitation would be this around 10 to the minus 11, and
Yeah.
Meg is aiming for 10 to the minus 14.
Oh, okay, very far. Okay. Is
But it
it
would
feasible?
cover any electromagnetic decay of muon.
Right.
So 10 electrons, 11.
10 electrons, yeah.
What was the model? What was the model? I didn't hear the model. I'll tell you.
I guess you could also do mu gamma gamma for some output that decays to 2 photons, which, as you mentioned yesterday, might be very hard at Meg. Well, my question was related to radiative pion decay. So could you do, and have you looked at pi to mu EE and pi to 3E, so it's 2 neutrinos, 1 neutrino, sorry.
Yes, and things like that could be done. Mainly the information will be coming from the tracking target when there are charged particles present. The calorimeter will have some tracking capability, but not a great deal. But quite a bit of information is available in the target because of the fine sampling of the silicon strips. So processes like that would be identifiable in principle.
But have you looked at what you can improve?
No,
current
we
vision?
haven't.
Yeah, okay, thanks.
Oh, it's a good idea. We will.
A really nice talk. I was just wondering, what's the size of the active target and how big could you make it if you really?
It's about 2 centimeters by 2 centimeters in area and 0.6 6 millimeters thick. So it has about 5,000 channels of XY alternating strips of one species.
What's the decision date for liquid xenon versus LISO?
We don't have a schedule really.
You're not doing it at Fermilab, so you don't have to have an idiotic schedule. Good.
Right. Basically, we have some questions that need to be resolved in simulation relating to the liquid xenon and pileup issues, because we want to go to very high rates. And in LISO, although the tests look promising, these were rectangular parallel pipette shaped crystals. And for Pioneer, we'll need very fine tapered crystals to make the spherical geometry. And will be an R&D issue that has to be resolved to see whether it's feasible. And we also, the crystals that were tested were relatively short, maybe 2/3 the length of what was required. So we'll need larger crystals. So there's still a lot of R&D issues that would have to be resolved.
But liquid xenon is basically the default at this point.
Pardon?
Liquid xenon is the default at this point. You
Yes.
have to come up with some really good reason and show that LISO would be better.
LISO may be less expensive or it may be more expensive. We don't really know what, so there'll be a cost issue also that needs to be resolved.
All right, if there are no more questions.
Yeah.
Okay, good morning. I'm Sohtaro Kando from KKJ Park. Today I'd like to talk about Muonium spectroscopy and interferometry. So I think all of you know very well, but I'd like to start from some introduction. So Muon is the second generation charged particle having charge mass like being shown here. So this particle forms bound state like muonium, mu plus, E minus, hydrogen-like atom. And also mu minus burns with nucleus and form muonic atom. So for case of muonium, the radius is almost equal to hydrogen. But for case of muonic atom, the radius is much smaller than ordinary atom due to the difference between the mass between electrons and muons. So this talk is mainly focusing on muonium, but I'd like to say something on a recent project regarding on muonic atom later. So here is two types of major classification of muon beams. First one is surface muons obtained around the surface of the production target. This beam has excellent energy monochromaticity and spin polarization, nearly 100%. But this is only available for mu plus because minus negative particles were captured and lost. And the other one is decay muons. In this case, both charges muons are available from Pion's decay in flight. So these are major muon beams used in meson factory or muon facilities around the world. So surface muon is an excellent muon beam, but there is some limitations. First one is the large emittance of the beam. So these panels showing some simulation results using Janford beamline to estimate, evaluate the emittance of surface muon beam. Under typical conditions, RMS emittance of the beam is 365 centimeters per radian. So this is relatively large for in comparison to other electron or proton beams. So this is originating from Pion decay, and muon it cannot be focused very well. And also there is large momentum spread. In this case, plus minus 4% of momentum spread is shown here. So these are intrinsic or nearly intrinsic limitation of surface muon beam. So we need more a brighter or cooler muon beam for precise measurements and also condensed matter measurements using thin film or sample having interface inside the sample. And also efficient muon cooling is essential for realizing muon collider and muon G-mass to JPark. And the other possible limitation in the muon beam at JPark is time resolution. There are two types of time structure of muon beams. First one is continuous, and the other one is pulsed. At JPEG, we are using synchrotron to generate produce proton beam. So the beam is pulsed, having a periodic structure as shown here. The period is 40 milliseconds, and each bucket has the time width of 100 nanoseconds. So in this bunch, many muons are included in this single bunch. So we cannot tell muons in this bunch one by one. So it is not good for experiment needs coincidence or some similar technique. So this is the limitation of pulsed beam. So for case of application, observing some fast process, such as fast spin dynamics in matter, there is a strong limitation or decrease of the Muon's decay asymmetry as a function of precession period. This corresponds to the fast time scale of dynamics. So pulsed beam is not good for a fast measurement or a high time resolution measurement. So there are currently there are 6 Muon facilities around the world. Rutherford in UK, PSI in Switzerland, and Triumph in Canada, and Fermilab in the US. And Japan is the only one country having 2 Muon facilities in one country. And also this RCNP music is a continuous source, and JPEG is a pulsed source. So Japan has a special opportunity to perform Muon experiments. So these are photographs of Muon facilities around the world. I have visited, I've also conducted some experiments in these 5 facilities, but I have never been to Fermilab. So the next time I want to visit Fermilab. So this is the JPEG, our facility, stands for Japan Proton Accelerator Research Complex. So this facility contains 2 types of links. First one is RCS provides 3 GeV protons for materials and life science facility. And the other one is the main link for comet, hadrons, and neutrino experiments. So inside of this building, there are 2 production targets. First one is for muons, and the other one is for neutrons. So we are using muon production target made of graphite, and there are several beam lines for muon experiments. So from now, I'd like to talk about the spectroscopy. So here is the energy diagram of muonium in 1s, 2s, and 2p states. So there are several transitions have been measured precisely. Here is the hyperfine splitting in the ground state, and here is 1s, 2s growth structure, and also there is Ramsey's and fine structures. So for case of the hyperfine splitting in the 1s state, the previous or the most precise result ever is this Los Alamos experiment obtained 12 ppb precision. So we are the museum collaboration aiming to measure this hyperfine transition with the precision of 1 ppb. So we are trying to realize a factor of 10 improvement. And also there is another project aiming to measure, determine the 1s, 2s transition frequency. So the most recent result is Rutherford 2000 result. 4 ppb precision was obtained. And now 2 research groups are working for improvement of this measurement. First one is Okayama University group. They are working at JPEG, and also MUMAS is measuring, trying to measure this transition with 40 ppt precision at PSI. So later in this afternoon, Paulo will talk about this. So here is the energy diagram of muonium under magnetic field in the ground state. So in the ground state, there are 2 states of muonium, a spin triplet and singlet. The energy difference between them is the hyperfine splitting. Under our magnetic field, due to the Zeeman splitting, the energy levels split into 4 sub-levels. So we can measure the transition here, and by taking the difference between 2 transition frequencies, we can obtain the hyperfine splitting in 0 field. So there are two types of measurements. The first one is direct measurement of 4.4 gigahertz at the zero field, and the other one is Zeeman spectroscopy to determine the hyperfine spectrum. So this is the experimental process for the previous experiment in the Los Alamos facility. So surface muon beam was irradiated to krypton gas target, and a microwave was irradiated to stimulate the hyperfine transition. And then they measured decay positron asymmetry from stopped muonium. So muonium rise hyperfine spectrum was measured with the precision of 12 ppb, and the muon to proton magnetic moment ratio was determined with the precision of 120. So the largest statistics was field uniformity, but the experimental precision was dominated by statistics. More than 90% of errors were arising from the statistics. So here is some examples of resonance curve of the hyperfine transition. So here is the comparison of theory and experiment. Here is the theoretical prediction. These numbers are uncertainty arising from the mass ratio and QED uncalculated terms and alpha. So the largest contribution is the mass ratio. So we need to improve the mass precision of muon, not only for precise comparison between theory and experiment. So now the theoretical predictions error is about 515 hertz. For case of experiment, this is the result. So 51 hertz, 11 or 12 ppb was reported, and also the mass ratio was determined with this precision 116. So if we want to compare theory and experiment, we need to improve theoretical prediction precision, but theoretical prediction is not limited by theory itself, but it is limited by experimental result of the mass ratio. So the mass ratio is key to improve or realize high precision comparison between theory and experiment. So the mass can be, so we need indirect or independent mass input for this comparison. So first candidate is Muonium 1s2s, and the other alternative I'd like to propose a Muonium interferometry later. So this is the experimental setup of our experiment, MUSEUM. MUSEUM stands for Muonium Spectroscopy Experiment using Microwave. So the experimental concept is almost the same as the Los Alamos experiment, but we implemented several improvements from the previous experiment. So we are going to use a high intensity pulse beam at JPark because the previous result was limited by statistics. So we need a high intensity beam. And also we place a segmented positron detector which has a good tolerance for high event rate. And also we improve magnetic field uniformity, and also field mapping technique is improved. So the target precision for the hyperfine splitting is 1 ppb and 12 ppb for magnetic moment ratio or mass ratio. So measurements under a zero magnetic field was done as a pilot experiment, and now we are preparing for high field experiment to realize the highest precision. So here is a photograph of our magnet and magnetic probe and positron detector. So this is the timeline of the project. The experiment was proposed in 2011, and we developed several prototypes for the experiment. And in 2016, we succeed in observing the hyperfine resonance and the zero magnetic field. And then we improved the approaches and precision step by step. And very recently, the beamline for this experiment was completed. So now we are going to switch from zero field test experiment to high field ultimate experiment. So here is some results obtained from zero field pilot experiments. Here is the Rabi oscillation of muonium as a function of time. So this is a time-dependent time changes of the muon polarization. So we apply a magnetic field to induce the hyperfine transition. So then a muon spin will flip as a function of time. So we can see this time variant muon polarization by irradiating microwave. And the bottom figure shows the resonance curve obtained by frequency scan measurement. So we determined the hyperfine splitting frequency with a precision of 900 ppb. The number is not so good, but this is important milestone for us. And the other improvement is analysis technique. We developed a new technique to analyze muon spin flip, not by taking time integral, but we can fit Rabi oscillation directly. So in this analysis, we integrate Rabi oscillation signal and obtained one data point at certain frequency. But we can directly analyze this Rabi oscillation with an appropriate fitting function and distributions. We can obtain the hyperfine splitting from direct fitting of the Rabi oscillation signals. So by applying this method and using additional data, we achieved 160 ppb precision. So we ended high field as a zero field campaigns, and we switched to move on the high field experiment. So this is the photograph of the experimental area for our experiment, and also DME experiment aiming to measure observe MUE conversion. So this is a beamline named H line, and this beamline provides 100 million muons per second. So this will be one of the highest flux pulsed muon beam source or beamline. So this beamline is dedicated for fundamental physics measurements, and the first beam extraction succeeded in January 2022. So now the beam commissioning is underway, and the museum will start our measurements under high magnetic field from the earliest case from January 2024. So very recently, we installed our superconducting magnet to the experimental area. These are photographs of the magnet and the installation taken in last month. So we just installed the magnet, and now we are going to ramp up this magnet for our experiment. Okay, now I'd like to talk about something about muonic atom. This is a kind of interlude. So first item is muonic helium. So we can use a museum apparatus for negative muon and helium gas target. In this case, a muonic helium is a three-body system, but like as shown here, alpha particle and mu minus and electron. So this is quite similar to muonium because the distance between mu minus and alpha is much closer than that of electron and alpha. So this can be regarded as two-body system, and we can perform spectroscopic measurements of this helium's hyperfine splitting with the frequency of this 464 megahertz. So this is quite similar to muonium hyperfine splitting. So we can use the same apparatus for measuring this hyperfine splitting. So this is good for testing three-body QED and also CPT invariance, because we can compare the results obtained by mu plus and mu minus. So here is the one of the first results of the hyperfine splitting spectroscopy.
Is there a binding state effect that renormalizes the magnetic moment?
Yes, there is correction terms arising from it. Yeah. So this is the result, and very recently, last month, the paper has been accepted by PRL. So this paper will be available very soon. So this project is a kind of spin-off of the museum and led by Dr. Strasser and Fukumura-san from Nagoya University are main player of this project. So the other topic is muonic atomic parity violation. So this is a new measurement, a new attempt to obtain determine the Weinberg angle by observing atomic parity variation in Munich atom. So in Munich atom is formed in highly excited state, typically saying the n equal 14 or something like that. And Munich atom cascade down to the ground state in very short time. But some fraction of Munich atom states 2s state at metastable state. So this 2s to 1s, one photon transition is optically suppressed. But we can observe this M1 transition if there is a parity non-conserving mixing between 2s and 2p states. So this is atomic parity variation in Munich atom. So this can be utilized to determine the Weinberg angle. So Weinberg angle is one of the important parameters of electric sector, but most precise result was obtained by cesium atom measurement. And the example or the results is relatively limited, rare. So I want to perform Weinberg angle measurement using second generation particle. So we developed the gas cell and detector for this experiment, and we have carried out several test experiments. And the other one is observation of atomic radiative capture. This is a process as shown here. This is similar to photon recombination or Bremsstrahlung, or this can be seen in a heavy ion collision. So this is a muon case of radiative electron capture. So this process is useful to observe atomic parity variation because this process can generate a 2s Munich atom directly without cascade. So here is the theoretical prediction of the cross-section. So we try to observe this process using fly path chamber and LISO-based calorimeter. And we obtained very suggestive results indicating some excess in the energy spectrum measured by calorimeter. So the detailed analysis is ongoing. So now I want to talk about muonium interferometry. So here is a reprise of the energy levels of muonium. So there are two major ways to determine the mass ratio, 1:2s and hyperfine splitting. But if we want to compare the results with theory, or in other words, if we want to test the standard model by these transitions, we need an independent input of the mass ratio from outside. So I'd like to propose a muonium interferometry to determine the mass of the muon. So here is an introduction of atom interferometer. You know, atom interferometer is interferometer using atom matter wave. So here is some example of Young interferometer, Manhattan interferometer. So we can construct this type of interferometer using some half pi powers as a splitter and pi powers as a mirror for optical interferometer. But for this purpose, this type of experiment can be done only by using low energy and bright muon beam. So normal or typical surface muons cannot be applied for this type of measurement or experiment. So there are several ways to obtain low energy muons. The first one is LEM at PSI. This is the method using a cold rare gas moderator to obtain epithermal muons from surface muons. The energy is 15 eV. And the other one is laser ionization of muonium, ultra-strong muons. This is the method at JPark. So in this case, we irradiate surface muons to our muonium emitter, such as hot tungsten or silica aerogel. And then muonium in vacuum is obtained from this emitter. So we irradiate two laser beams simultaneously. One is 122 nanometer light to excite muonium from 1s to 2p, and the other one is 355 nanometer for ionization. In this case, the energy of released muon is at room temperature or target temperature. So these two methods are promising ways to obtain slow muons. And also in this workshop, Angela talked about the MUCOOL as a novel technique to obtain low energy muons. So here is the overview of our facility, ultrasound muon facility at JPark. We use high intensity pulsed surface muon beam named the super omega beamline, and we irradiate surface muon to hot tungsten at 2000 Kelvin. So this is good for muonium emission in vacuum. So we irradiate two laser light to muonium in vacuum, and released muons are accelerated and extracted, transported to two experimental areas. First one is U1A. This is for condensed matter physics or ultrasound muon MUSE. And the other one is U1B. Here is a test bench for realizing testing transmission muon microscope. So this is a timeline of the ultrasound muon project. So in 2016, the first ultrasound muon generation at JPark was success. And then 2 years later, first MUSR was performed. And more 2 years later, we succeed in multi-layer ultrasound muon MUSR. So we started to use sound muons for material science research. So here is some specifications of the beam. The flux is 300 per second. The time width is about 2 nanoseconds, and the spatial spread is also 2 millimeter for each X and Y directions. So the beam flux and width are shown here, and these specifications were quite enough to initiate MUSR measurements for condensed matter research. So we started the first scientific program using slow muons for studying thin film sample. That we need more intense and brighter muon beam for interferometer. So I propose this scheme to obtain a very bright slow muon beam. So this is a conceptual design of multi-stage muon cooling. The first stage is made of LEM concept, low energy muon concept at PSI. So we use a solid reaction modulator to obtain epithermal muons from this. And then epithermal muons are focused by electrostatic lens and converted in muonium and ionides. So this is a good scheme to obtain very bright and slow muon beam. So now I'm working for realizing this. So here is the last topic of my talk. This is a scheme of Ramsey board interferometer to measure the muon mass. So we use muonium, and muonium is excited to 2S state by 244 nanometer laser. And then we irradiate a pulse train of laser lights. So this optical pulse sequence will produce 2S and 15P states of muonium in this way. So we can measure the interference of these two states of muonium at the detector position. So this is a good way to determine the mass of the particle in the form of H over M. But no experiment has been performed for muonium, of course. There is an example of a hydrogen atom. So I try to figure out the possible sensitivity and the potential problems of this interferometer for determining the mass. So here is a little bit more details about the principle of Ramsey board interferometer. So there are several trajectories of muonium in interferometer, and we can take the phase difference between different trajectories, and then we can determine the mass of the muon in this way. So I don't talk about the details, but this type of pulse train measurements are relatively well established in normal atomic experiments. So I'd like to introduce AMO physics technique into muon physics to realize high precision measurement. So the goal of the precision is 1 ppb. This can be realized by applying 10 pi pulses irradiation to expand the phase difference. So this is the goal of the project. So now I'm working for several R&Ds for simulation of muon production or target chamber or beam transport optics. So this is the summary. At JPark MUSE, the museum experiment is in progress for measuring the muonium hyperfine splitting. And muon cooling and application of quantum techniques will bring a breakthrough. So a new type of muon mass measurement using interferometry is under study. Thank you.
All right, do we have any questions?
Thanks. I really like that talk. I feel like I haven't been paying enough attention. I want to focus on the atomic parity violation.
Mhm. Yep.
So, so I did an experiment in the 90s where we got
Mhm.
almost 4 sigma. So I was NUTEV,
Mhm.
right? When we got like a significant discrepancy, which could have been interpreted as G Fermi neutral current over G Fermi charge current, isn't quite right. It was promptly ignored because it didn't agree with Susie.
Mhm.
So, you know, I've never really thought about this, but there are 2 things I think about right away. So this must be a very similar Q squared to the cesium experiment. So now you're really checking muons versus electrons in such an experiment. Is that correct?
So muon to electron.
Yeah, muon to electron. You're checking second generation.
Yes, yes,
It's got to be a similar Q squared.
yes, yes, similar Q square. Yes,
Yeah.
at MEV
Right.
energy
Okay.
scale.
Good. I just want to see if I understand. So then, again, given that I've never thought about this for 5 minutes, which is my fault. Okay. So if I were going to do a capture experiment, I mean, these are negatives. So
Yes.
they're going to get captured. So every piece of garbage in the world is going to get produced when they get captured.
Yes.
How do you get around that?
Yeah, there are several ways to select a target for the experiment. So I selected low-Z material. For example, C, carbon, is selected as a target. So in this case, the capture is not a serious problem. For case of heavy elements, there are several difficulties, but at PSI, people are working for this type of experiment using krypton targets.
Okay.
And also, it is feasible.
Okay. I just want to add that the PDG, which I'm still angry about, blew up our errors because they didn't agree with other experiments that they wanted, they thought had to be right. So the plot that they show is not what we published. And I'm still annoyed at Jens Erler about that. But I just wanted to say that. Okay. Thank you. Good, really good talk.
So when you apply the magnetic field to this hyperfine lines, you get like 4 lines, right? I mean, four different states. Like, how many transitions between these states can you measure?
Yeah, we measure 2 transitions.
Can you measure more, actually?
I think this apparatus is only for this experiment.
Mhm.
So, but we can change the B field, and also we can measure some, for example, this transition between 1 and 2 and between 3 and 4 can be measured around here. But under a low or medium field, we may measure the transition between other states.
So I'm just getting to the point of this muon force, right? With the pseudo magnetic field acting on the muon. So if you measure all of them, then you'd be able to isolate this effect.
Yes, I think this experiment is quite useful to such exotics or new forces. So we can we want to consider the possibility of such a kind of circuit. Thank you. Yeah.
Paolo Crivelli has a question on Zoom.
Mhm.
What is the limitation for the muonium interferometry to a mass determination at 1 ppb?
Yes, that is very good question, and that is under study. Sorry, at this moment I don't have a concrete number or statement, but possibly the result will be limited by the number of muonium statistics. And also there are several items to be careful. For example, the precision of pulse train control, but I have to study about it.
Okay.
So similar talk, how many muonium needed for atomic parameter? And then I'm sort of ignorant. Why is it a 15p? That's
50 EV?
Yeah, 15p state or something. Why?
Yes, this is how to say, this is just determined by laser light frequency. So we can choose another state. That this I followed this hydrogen photon spin echo measurements. So this is not how to, this is, 15p is not essential. We can choose, but I just follow this hydrogen example.
How many million? You don't need many.
I think this precise interferometry is not require numerous numbers of muonium, but a minimum requirement. There is minimum requirement. So now I'm calculating the minimum requirement of muonium flux by simulations.
Any final questions?
What is the plan to measure the hyperfine splitting? You are sort of have a magnet now. So what is the sort of schedule? Do
In
the
our
measurement?
case, January, next January. Yes.
Okay, let's thank Sohtaro again. And we'll reconvene at 11.
So what's the PDG explanation that you have not included?
So, yeah, it's just say more. Yeah, you know, it didn't agree. He explains to me when he got very aggressive about it. And I'm like, my result is all that's the same down here. You know?
Yeah, we think for like.
Yes.
Maybe exactly.
That's okay. Yeah, I just got it right outside. Yeah, because we measure those strange C.
And the.
That's a much harder measure. So-
That's
Yeah, I mean,
I still have to use those available now. I didn't see him. First they got the bus because one side efficiency. You know, we did it, I suppose. None of the models predicted anything near.
I see.
Now, Tony Thomas has some set of models which post hoc you got to add up to exactly explain the effect.
I don't know what.
And it was really
How old
funny
is he?
because, so he wrote a paper, I found a mistake. in his
Six.
I think he's older than me. Change.
Oh, okay. 7. I'm sorry that. I just as well.
I would say he's in.
Late 80s.
I mean, it's probably better.
I'm
Maybe
sorry.
in an interval of about the same.
Yeah.
So it was one. You know, so maybe.
Because he was, I'm confused.
It's
an older person.
Yeah, it's
harder. I'm sorry that maybe I missed about that.
At least 10 years.
Yeah, at least I missed.
Yeah.
Just got
I don't think it's in Australia, right?
Yeah.
They have this complex in Australia that you know, like their best fit is many thousand miles around them.
I mean, so it's basically, which, you know, but.
Yo. Yo, yo.
Hi, Michael. Are you there?
Yes, hello, good morning.
Hello. So can you try to share your screen?
Yeah, let me try that. Okay.
Yeah. I don't see your slides. Great. Okay.
And
Yeah.
also the cursor. Yeah, okay, great.
Yeah. And then, so can I also see that I'm writing something on the screen?
I can see a head, yeah.
My head?
Oh, yeah, okay, you just wrote 10 minutes, yeah. I can see that.
So I will notify you the time, like 10 minutes left and 5 minutes left and 0 minute, just writing down on some corners of the screen.
Yeah, okay.
Okay.
Thank you. Let me know when it starts.
Thank you.
Are you just gonna write on your? Yeah, that's fine. I can also write. I'm gonna take care of it. I'm gonna go your side all down. My channel is gonna be like. The handwriting.
Oh, that's beautiful. Yeah, exactly. But that's fine, I think. Suppose you can ask some.
Well, Michael. We'll start shortly,
Okay.
maybe in 5 minutes.
5 minutes, yeah.
Yeah.
4 minutes.
I hope your exam went well.
Yes.
Sorry for not that you couldn't come over. That's
Yeah, it's too bad.
I think
But apparently there's another second pressing item is the NSF deadline on Tuesday, which also keeps me up at night these days.
If you put his screen in a corner and on your computer right under that corner, then the audience will see it. Only you can see it, but
Audience can see it, I think. It's fine.
yeah, it's not a
Yeah.
big deal. And I think that's
It's not weird.
there's an X.
Yeah, oh yeah, it's there, it's in its position.
Always happy.
Sort of happy.
Love you, happy.
By the way, our friend from Red Top is already complaining.
I would have been surprised if he wasn't.
Let the wars begin.
Peace in the floor. Okay, so I think we can start a second session in the morning. So the first speaker is Michael, and then he's going to tell us about MUSE at PSI. So please.
Yeah, thank you very much. And I'm feeling very sorry that I cannot be there in person. And it's partly related to our final exams, which were just yesterday. And I also have a pressing funding proposal deadline. And I'm getting a lot of nails plugged in. So, but I feel very honored for the invitation by Maxim to talk about our MUSE program at PSI, the Muon scattering experiment, which was designed to address the proton radius puzzle that has been around for a bit over a decade now. So here's my layout for the presentation. I will remind you of what that proton radius puzzle was, an above 7 sigma discrepancy between measurements of the proton radius of different methods. In this context, I will discuss the aspects of lepton universality, as well as two-photon exchange that were both prominent possible explanations, and how that is related to the MUSE experiment that I will show you some details of the apparatus, but also discuss the sensitivity, as well as give an overview of some initial data that we have now and the status and outlook. All right, and all that in 25 minutes. So let's get on. So this is a plot that you've probably seen oftentimes, even if you're not from the nuclear community. That is the proton radius puzzle. You see two prominent values. One is gathering many measurement groups at about 0.88 femtometers, whereas there's these super precise measurements from the muonic hydrogen experiments in 2013 and 2010 when it was released for the first time. And at the high point, it was close to 8 sigma of discrepancy between the two error bands of the two groups. This was reduced a little bit to above 5 sigma with the CODATA 2014 assessment that came out in 2016 or so. But at that time, it was still an above 5 sigma in 2016. That was not the only muon-related anomaly that we've been seeing over the years. There's the famous G-2 that you've probably been discussing here. That is the plot from the latest release of the data. If the theory band is taken as it was 3 years ago, it would also be approximately 5 sigma, although there's now theory floating, and it could diminish the discrepancy. But it's highly interesting that these anomalies pop up in the muon sector. And speaking of muon anomalies, there's also had been a muon electron sector anomaly in B decays to charged kaons reported at LHCb a couple of years ago. And as of 2 years ago, this even made it into a Nature article at an about 3 sigma level at the time. However, at the end of last year, all of that anomaly has diminished and has disappeared for more data being analyzed and an additional channel, and also with improved analysis techniques. So this has been in motion. So for coming back to the proton radius, this is an overview of various measurements and projections. You see in blue is the CODATA assessments over the years. In green is hydrogen spectroscopy, which used to be large for the proton radius, but there have been a few new measurements that favored also a smaller radius around 0.84. Most recently, though, it's rather falling in between, and what that could indicate is that there are some understood systematics in the hydrogen spectroscopy. The electron scattering are in black, and you see that there's also a recent data point that favors a low radius, a small radius. So that also indicates that there might be systematic effects at play in the electron scattering method. So all of this is still a blurry picture, and it cries for more and better and precise data. And there's currently 4 projects on the market that all will have new data in the near future. So is the puzzle really solved with explaining systematics and giving all the right to the precise muonic hydrogen spectroscopy? Well, here's the conflicting data sets between the new data point from PRAD Jefferson Lab that favored a small radius and the bulk of electron scattering data from MINES that had favored a larger radius. And you see that these curves are discrepant, in particular at modestly low Q squared. And this is clearly an issue that is not understood. And more experiments are needed to shed light on this. And the electron scattering experiments using initial state radiation or ultra low Q squared in Sendai, as well as MUSE with a large angular coverage, should be able to address this. So for the MUSE experiment, some 12 years ago, there was a workshop in Morocco that Ron Gilman, Jerry Miller, and myself attended. And there was a wine and cheese reception where we contemplated about what to do about this novel proton radius puzzle. And we realized at the time that there had been spectroscopy now at good precision between regular hydrogen and muonic hydrogen, and electron scattering had been done for many decades. However, that it was lacking a precise muon scattering data point. It had been attempted in the 60s and 70s, but not with good enough precision to make a statement in this context. So this created the idea of MUSE. You could do this at high or low energies. We favored a low energy setup and designed an experiment with secondary beams that eventually would be able to probe a lot of things. Because if you use secondary beams, you can have both E and mu in the beam, and you can also pick the polarity of the charge. You can have positive or negatively charged beams. And this can basically probe all the possible explanations that were on the market. So there could be fit procedures not precise enough in electron scattering, given by the limited range of Q-squared coverage. MUSE has a large Q-squared coverage and can make a statement. There were effects associated with two-photon exchange or proton polarizability effects that were also predicted to be possibly large for the muons. That could be a possible explanation. This will be actually probed by the MUSE experiment, and we can make a sub% level statement about that. And of course, having mu and E in the same beam opens the door to probe really the Lepton universality aspect and to establish whether the electron and muon scattering is really universal as it should be in the standard model. So going on to MUSE, it is situated at Paul Scherrer Institute. There's the roof of the high intensity proton accelerator, which is a cyclotron that provides secondary beams of E pi and mu to various places. So we can have simultaneous separated beams of either positive E pi mu or negative E pi mu impinging on a liquid hydrogen target by our design. The separation will be established with time of flight techniques, and the goal is to measure absolute cross-sections in a bread and butter scattering experiment. At the same time, because we have all species in the same beam, we can form universality ratios separated by charge to cancel certain systematics. But the overall idea is if the radii differ by as much as 4% as suggested by the radius puzzle, you should see discrepancies in the form factor slopes for E and mu twice that much, or cross-sections even twice that as these quantities propagate. The beauty of MUSE is that we can disentangle possible effects like two-photon exchange and form charge symmetric cross-sections, as well as E over mu ratios with the two-photon exchange is cancelled out. So MUSE would cover various beam momenta, we call them, not energy, but momenta. It's a magnetic chicane that selects the momentum of the particles for a broad range of for momentum transfer given by the detector acceptance. The beamline at PSI is shown here. You have the primary protons. They have about 2 milliamps or megawatt beam on a production target. This is then selected in a double C chicane. There's an intermediate focus point with the dispersion where we have slits that we can select momentum bytes for, and then deliver the beam with more quadrupole focusing to the experimental area on the top left. So these beams have typically intensities at the level of a few megahertz. We can control the intensity with the beam with slits here and with apertures in front of the first C. The understanding of the beam has been really pushed hard by all the committees using various codes to understand the beam properties and how the beam propagates. And this is now really at a high level of understanding and has been published. The arrival times of the particles will be separated by several nanoseconds. As you see here, there's E, pi, and mu arrival times relative to the RF clock, which is 50 megahertz. So you have every 20 nanoseconds a rollover here. And the momentum is chosen in a way that the peaks would not overlap. And that is important because we need to have at the trigger level suppression of the pion-induced scattering events because of the strong interaction cross-sections being so large compared to the electromagnetic. That is actually necessary. The layout is shown here. So you have that secondary beam comes in, you have a scattering chamber with target, like usual in electron scattering experiments, and then two arms of large acceptance scattered particle systems with straw chambers and scintillator walls. There's some beam diagnostics upstream and downstream of the target. In particular, upstream of the target, because it's a secondary beam, we need to have methods in place to measure both the arrival times as well as the spatial locations and orientations of the trajectories in order to form the baseline of the scattering angle measurements. So we have two trackers, gem trackers in the beam, as well as straw trackers for the scattered particle, and the common vertexing is then applied to identify scattered particle events. The whole setup does not use any magnetic fields, which makes it delicate for radiative corrections. There is a colorimeter downstream, which is in use to control some of the initial state radiation corrections, which would otherwise become excessive. And plus there are some other measures in place. The beamline elements are shown here. This is a set of fast scintillator counters with PSI-PM readout, as well as GEM telescopes that were inherited from the Olympus experiment. This has before also been my responsibility to provide the GEM detectors for tracking. Then the target chamber is shown here. You see the liquid hydrogen target in the center. There's the picture of the cell. This can move up and down. In front of the target chamber is a veto counter ring with a slightly smaller aperture than the size of the cell in order to suppress any triggers originating from scattering outside of the interesting region. The scattered particle detectors are shown here. The time-of-flight scintillators are JLab Hall B style from the University of South Carolina group with very good time properties, better than 100 nanoseconds time resolution. And the straw chambers were built by the Israeli groups at Hebrew University in conjunction with Temple, straw tube trackers with about 3,000 straws. The whole setup for calibration purpose is sitting on what we call a rotating table. So there's a donut down there where the target is inserted onto, and sitting on this rotational table, or we can rotate this table with the triangular shape here, and also retract the beam tracker so that you can actually rotate the scattered particle detectors dowel pinned into the beam orientation for relative calibrations. And then we rotate them back by a known angle and have the calibration for the scattering angles. electronics is modern electronics based on FPGAs. I don't want to say much except for the trigger electronics that select events without pions. So you see here the arrival spectrum with pi, mu, and e, and with the pions suppressed at the trigger level, which is achieved also by an FPGA. And that reduces the trigger rate to the interesting level. Here are some more modern pictures of these measurements. You see the red one has the pions suppressed. All right, there has been a simulation package being developed by the South Carolina group. And what you see here basically is scattering, the elastic scattering EP and the Möller scattering EE. There's a region where Möller backgrounds become important, and we have identified that the scattering angular range should not be below 20 degrees in order to keep the Möller backgrounds under control. And under these conditions, scattering angle ranges from 20 to 100 degrees. You see here a vertexing plot distribution where you can see simulated events generated from the entrance and exit windows, as well as the entrance and exit wall of the target cell, as well as a full versus empty target simulation. This would then allow for a net yield assessment by a subtraction method. So this was all the simulation done a couple of years ago when we designed this. Now, yeah, I've noticed the 10 minutes. Thank you for the reminder. So here's this plot again that shows the discrepancy between PRAD and MINDS. And in yellow overlaid here is the error band projected for MUSE, and we should be able to distinguish between those data sets. There are more projections here for the plus over minus 2 photon exchange effects for the muons. This is showing the statistical precision that can be achieved in the course of the experiment, as well as calculations of the 2 photon exchange effect. These are generally predicted to be small at the sub% level for electrons, and even smaller for muons, as calculated by Tomalak. For the universality ratio, we can form ratios between EP and mu-p. You also see statistical precisions will be better than percent for this. For the radius extractions, the extraction of the proton charge radius from form factor fitting method, etc., will be compatible with previous electron scattering measurements. But if you combine the electron to muon difference to probing the discrepancy of the charge radius, the difference between the muonic value and the electronic value, which could be up to 0.04 femtometers, then there are certain cancellations that make the MUSE projection even more precise. And if it becomes true that the discrepancy is as large as had been observed, then MUSE could reconfirm this at a above 7 sigma significance level. Okay, so before showing some data of MUSE, I want to mention that all the MUSE data are being blinded in the analysis stage of tracking, where a randomized oscillating function is used to suppress certain fractions of tracks in the accounting of the track samples. Both data and simulation are treated the same way at this stage, so they all have blinding applied individually and also by species. And the size of the blinding range is such that it exceeds the expected size of any physics effects that MUSE is trying to measure. So it affects data to Monte Carlo ratios, TPE ratios, Lepton universality ratios. This is just to accept. And then all the data shown are blinded, as you will see. There was electron scattering from carbon initially tried in 22. This is a vertex plot showing the horizontal versus longitudinal coordinate. You see various locations which have vertex origins for tracks. The interesting region is this. The carbon target could be seen like this. And in this holographic view of event vertices, you could recognize the shape of the carbon target with ancillary elements in the density distributions of vertices. So that gave us confidence that we can do this. Monte Carlo has been developed in parallel. This is blinded, showing good agreement for the angular distributions. Then we went to hydrogen. This is 22 data at 160. You see the hydrogen cell shapes on the left, and the encircled area in the middle is the region of interest. At that time, there was also still excessive backgrounds produced in places that are not the target, but close to the target and would be identified. This gave us this vertex distribution where you see a full versus empty target distribution. This is still large backgrounds that were more pronounced at forward angles. This has improved now in the 22 data. Sorry, go ahead to this plot. So in 23 data, this is data taken this year, with improved vetoing and improved vertex analysis, the background yield with empty target is now seen here in blue and in orange for the two empty cell types that there are. And the shark fin shows the full target yield in terms of these vertex distributions. So this gives us now a good clean extraction of production yields. And now you can look for extractions of preliminary cross sections. This is done here for the, sorry, the bottom row is negative. These are typos. So positive E, mu, and pi proton scattering, and on the bottom it's negative. You see the comparisons of extracted data normalized to nominal acceptances and target thicknesses, the usual traditional way. And note that this is blinded, but there are no order of magnitude outliers. This is roughly understood. And now also supported by the Monte Carlo approach, which is also still very preliminary. Not only is the Monte Carlo blinded, it is also still without radiative corrections and therefore still not really realistic. There have been two independent analyses quite progressed so far. Win Lin is a PhD student from Rutgers who's graduating now, and Yevgen Lavrukin, whose data is shown here, is from University of Michigan, a postdoc. So getting closer to the end, I show you a few pictures. This is from the 2018 to 22 installation and commissioning period. You note this was also during the COVID-19 era, and there was a slowdown of the overall progress due to traveling constraints. And the commissioning really took until last year, and only from this summer, really, we had a good start of production data taking. Total data should be 12 months over the period of 2 years. So far, we've had about 4 months of data taking this year, and we anticipate more. Here you see the platform hanging on a crane. So ever so often, the entire MUSE experiment needs to be craned out and in to the PyM1 experimental area at PSI, as this is a multi-user beamline. And you see the complexity of the apparatus here, just floating in the air. And so for the timeline and status, the proton radius puzzle is still not solved 13 years later. Of course, it's not as binary as it used to be, but more blurry. But it is important to do the MUSE experiment because the Lepton non-universality aspect is still in the center of interest of all beyond the standard model effects. MUSE was proposed in 2012, so it's been a bit over 10 years now until production running. Funded since 2016, construction then started in 16. Commissioning ran from about 18 to 22, and so far we've had about 5 months of production data. Current status, so 14 weeks were taken since June of this year. An additional 3 weeks are ongoing right now in December. We are in December now. There was some initial data taking at 115 MeV over C. That was the lowest momentum setting last year. This year, we've been focusing on the medium and high momentum settings. There's only 3 momentum settings overall, and data are being analyzed. And we anticipate to continue data taking next year and also during 25 before we have everything. But so far, so good. There have been several publications that I've listed here. The most recent one is about blinding. The previous one was about the beamline characterization. These are significant. There was various NIM type articles on various components of MUSE. And I'm closing with the list of our collaborators from a large number of institutions, but mostly led by the US. So thank you very much, and I'll be happy to take questions.
Thank you. So questions?
Thank you for the nice talk. Can you comment on your resolution in angle? I didn't see it in any of the plots, so scattering angle.
Did you say resolution?
Resolution in scattering angle.
This is driven by multiple scattering. I didn't bring this plot, but yeah. So the multiple scattering is at the level of 10 millirads, and all the detectors would be capable of measuring with a higher resolution than that. And currently we have not quite achieved that, as this is still pending improved optical survey. And there's a whole procedure mapped out how to optimize this ultimately. And the resolution goal was chosen in conjunction with the scattering angle range starting at 20 degrees to have then the multiple scattering, or how wrong you are with the mean value of any scattering sample measurement, that is what propagates into the angular distribution. So we designed it in a way that the multiple scattering false average stays below the systematic goal of the experiment, which is at the 0.001 femtometer level for the radius.
Thank you.
I have a super naive question. So our colleagues at JPark are developing the Muon beam with unprecedentedly small emittance. Would this potentially be helpful in the scattering experiment if you have like a super high definition of the Muon beam?
Depends on what energy and intensity they can provide.
I guess they're thinking of 300 MeV kind of momentum.
Oh, really? And with I suppose 10 to the 6 muons per second and more.
So in that range, this is the beam that they want to use for G-2, but potentially that could be also applied to muon scattering.
I've not been aware of that, so thank you for pointing that out. That is rather interesting. So that puts us in the right range. There has been some discussions with Ron about parity violation in muon scattering, which at the conditions of the current Pion 1 beam is not accessible, but maybe in a cold muon beam of that type that you described.
The same beam can be manipulated with because it starts from the muonium. You can manipulate the spin, sort of you can flip the spin. So it would be ideal for the parity violation studies.
That's very interesting. Yeah.
Any more questions? If not, let's thank Michael again.
Yeah. Thank you.
Yeah, so Balint, are you there? Yes.
Yes, can you hear me?
Yeah, we can hear you and we can also see your screen and the console.
Oh, great, thanks.
Okay,
So let me know when I can.
yeah, just to keep the time, so I will write down like 10 minutes and 5 minutes on the screen. So, okay, then maybe you can just make it to the full screen. Yeah, okay, great. Okay, so the next speaker is Balint from York University, and he's going to tell us about sensitivity potential to a flavor changing scalar bosons where DUNE and Na64. So please.
So thanks a lot for the invitation from the organizers, Maxim. I apologize that I couldn't be there in person, although Toronto is actually not far away. My wife is about to go through a two-body decay, and one of that decay product is going to be a small baby, so I have to stay home and be in high alert. So with that, I would like to go on to my slides. Oops. All right. So a small outline. So this is a standard sensitivity study mainly for potential searches for charged lepton flavor violation in two different experiments, Na64 and DUNE. And I will go through a bit of mandatory motivation, then present the model that was actually proposed by the organizers themselves, Yohei and Maxim and other colleagues, and then also show that there is a similar sensitivity perhaps for other types of flavor conversion at Na64, and then I will conclude my slides. So this is a quick motivation. We know that dark sector physics could manifest with the or beyond standard model physics could manifest in interactions with leptons. We know about the existing discrepancy between theory and experiment for the muon magnetic moment. And we know that lepton flavor is conserved with the massless neutrinos. We know that there is neutrino oscillations, so that means neutrinos are not massless, and we also know they are non-degenerate. And so this suggests there is lepton flavor violation in nature. However, charged lepton flavor violation hasn't been observed yet and is heavily suppressed by the standard model. So any observation of that would be any sign of new physics. And if there is a lepton flavor violating interaction realized by nature, yeah, it could be mediated by some sort of new physics. The dark sector particle feebly coupled to the standard model particles. And in this nice workshop, there was already many examples of use of muon beams to search for signs of charged lepton flavor violation. I don't want to go through all the list because you have heard about them. I would like to focus on the muon beam on target type of experiments. Two of those is Na64, which actually operates both with an electron beam and the muon beam, but this time I'm only focusing on the muon case. And DUNE and or hyper-K, although I'm going to only focus on the DUNE scenario. Of course, there are other experiments in the pipeline that are coming. I apologize if I forget some from this nice list. So the model that's been put forward recently by the organizers of this workshop is scalar bosons that can mediate flavor changing interaction. And here's the Feynman diagram shown on the slide and the interaction Lagrangian. So it's basically scalar coupling to fermions, and certain vector and axial vector couplings are free parameters of the model as well as the mass. And a very interesting feature of this model is that if the mass of this boson would be such that two-body decay is not allowed to take place, such that the mass is either smaller than the sum of the two final state leptons or larger than the difference of the two, then that means that if two-body decay is forbidden, then it will have a long lifetime. And experimentally, it's interesting because that could lead to macroscopic propagation after the production. So certain features of this macroscopic propagation could be used as a way to see if this is realized by nature. And so the model also defines a benchmark parameter target region that could explain the Muon G-2 anomaly. And it's shown on the left side in the parameter space of the axial and the vector coupling parameters for certain mass scenarios. And I would like to mention that because in this particular case of the muon converting to a tau, that I probably hasn't highlighted that, the mass range of this 5 boson would be close to the mass of the tau, basically. And the paper that I already mentioned highlights some of the existing limits from Newton and Charm for the mass and the coupling strength parameter space, and some of the projected sensitivity limits for the SHIP experiment that has been derived for muon on target direct electroweak production or heavy meson decay cases. And we, as I'm a member of NA64 and DUNE, we did together with the NA64 colleagues actually, and DUNE colleagues studied where the sensitivity of DUNE or NA64 would lie in this parameter space, how much could we find, how much could we push the limits. And so for that, well, one thing is there's obviously a threshold for this production. If you assume, again, the 5 boson mass is around the tau mass, then it's at around 3.8 GeV, above which the cross-section rises very steeply. And as I said, it has no two-body decay modes. So the one, in order to be compatible with the model and the limits in the paper, we're also focusing on the decay mode of this 5 boson to a 4-body final state, in particular muon plus, muon minus, and 2 neutrinos. And yeah, if one calculates, again, using the 4-body final state integrals that were also in the paper, then one gets basically tens of kilometers of lifetime, slightly changing as a function of the mass of the boson. And so we use this sort of process as a benchmark for muon on target experiments, which are basically experimentally realized by having a very precisely measured incoming muon beam with known energies and energy distributions. And then after a beam dump, basically measure the outgoing particles very precisely and see if there is a missing energy. Or alternatively, one can also just simply look for excess above a certain background after the dump. So the two experimental scenarios, as I mentioned, would be NA64 mu, so that uses a high intensity 160 GeV over C muon beam at CERN with a lead or tungsten target. And DUNE turns out to be also a muon beam dump experiment. So it actually has a byproduct. It's created as a byproduct of producing a neutrino beam by colliding a proton beam on a target. And there is a beam stop made of steel for the muon beam. And that's basically our target in this case. For both experiments, the signal yield can be calculated from the flux of the bosons at the production and having them fly out. In the case of NA64, of course, we don't see the boson, so it's an invisible mode search, while for DUNE, we actually want to see it, so it's a visible mode search. Sorry. All right, so this general approach of muon beam dump to search for hidden sector signs, signatures, is actually being used also for looking for other types of interactions. And so here I just wanted to flash a list of other types of models that could be tested: milli-charged particles, search, deep elastic scattering, flavor conversion with leptons, vector polar interactions, and so on and so forth. And yeah, the bottom one is the one that I'm talking about in this talk. So first starting with NA64 mu, so it's a fixed target experiment, as I mentioned, looking for dark matter portal interactions using 160 GeV over C muon beam. And basically the incoming beam is very precisely measured with scintillators, veto counters, tracking system, dipole magnets, and so on. So it's very, very constrained. And then if there is some sort of a new physics process after an interaction on a electromagnetic colorimeter as sort of an active target. The outgoing final state muon is measured as well. And if there is any missing momentum or energy, that could be a signature of new interactions. And so, as I said, this is mainly the invisible mode search. And because in this process, if you look at the Feynman diagram at the bottom of this slide, you see that the muon converts to a tau. The tau decays very fast. And so what we see is actually the leptonic final state, or what we trigger on is a leptonic final state from the tau decay as a sort of a proxy, while we don't see the outgoing phi boson. And by the way, for much more details about the NA64 experiment, you will hear in Paolo Crivelli's talk after the lunch break. So once we have the initial state well defined and this process ongoing, as I said, the final state is a single scattered muon that we try to trigger on with the off-axis trigger system. And we also realize a physical trigger to look for basically events that have less than 80 GeV in the final state. And I mean, one can just basically sample the phase space of this process and use rejection sampling to look at the final state energy distribution of the tau and the phi boson, which is shown on the bottom left. So one can see that the energy distribution of the tau is basically exactly in this range of the general target physical trigger region of the experiment. So this blue distribution is between 0 and 80 GeV, and the red one is the energy of the phi boson. And on the right-hand side, what you see at the bottom is a typical feature plot that we usually use to define the signal region and the various standard model background regions. So what you see is horizontal axis is the outgoing final state muon, reconstructed muon momentum, and on the vertical axis is the total colorimetric energy deposited in the ECAL and the HCAL, which is also after the ECAL system. And for standard model events, if the incoming energy and the outgoing reconstructed energy and the momentum sums up to be the same, then we get this diagonal line in the middle of this plot. I don't know if you can see my cursor. You get this vertical line, this bar of events when the event, when activity was only in the hadronic colorimeter. And you see basically that there is a peak. It's a logarithmic scale plot. There's a huge minimizing particle peak just from the standard model background. And if there is any sort of missing energy, we expect the signal to lie in this blue region. And for this particular model, it's very clear that it will be there lying there. So if one just takes a very naive assumption of this process and assumes the collected data of roughly 3 × 10⁻13 muon on target that is typically reachable within the lifetime of this experiment, and if we allow some optimization on the target material and length, also if we neglect all sorts of detector effects in a sense of reconstruction, and we only and we allow multiple decays of the tau, then one would end up with a 1 meter target length. One could be able to approach this target region defined by the Muon G-2, and if for some exotic scenario of a 5 meter long tungsten target, one could even completely cover it. Of course, this is just the idealistic scenario. In reality, it's much more complicated. There are a lot of challenges associated with this. So, for example, the muon beam in the intensity at the CERN M2 beamline, of course, has a certain amount of parameters. Mainly can deliver 2 × 10⁸ muons per spill. However, NA64 at the moment is only capable to operate 10⁷ muons per spill. In theory, assuming 10⁻11 muons on target per day with 80% duty cycle, this actually assumed total collected data could be realized or could be reachable within, let's say, 50 days. But this would require an upgrade to the trigger system, which actually is planned during the LS3 shutdown in order to be able to cope with 6 times 10 to the 7 muons per spill by the electronics, but also with the higher intensity, of course, one will also have higher backgrounds. One of the assumptions is that I made is that the tau lepton can decay to any final state, but of course we can mainly only trigger on the leptonic mode to decay, which is like 18% for the tau. And the other hadronic final state, of course, would also fly away. So that would be another type of optimization that would be required in order to see those. And as I said, the target needs to be several meters long in order to be able to profit from that length. And there is also in the pipeline a new tungsten colorimeter test in 2024. So some of these steps would mitigate these challenges and difficulties. So I'm trying to speed up because I see I only have 10 minutes. And so some of the students in our group from ETH Zurich, actually, whose name is outlined on the slide, actually started to work on a full simulation with the Giant 4 package. And so what's shown in this slide is just simply what we would see from the standard model background on the top 2 plots before serious selections. So on the left is just simple beam quality cuts and some sort of a veto activity cuts. And on the right, you see that if we actually require a trigger and MIP compatible events, then basically all the background can be eliminated. And on the bottom, you see the same for the actual model case. On the left, you see that the populated region is basically this low muon momentum region. And this, after all the cuts, we would see the population there. So we would have, of course, some certain signal efficiency, but we could maintain it to some higher level. So the students actually implemented the current NA64 muons setup where we would be right now with our target thickness or target length, which is only effectively 25 centimeters lead. And unfortunately, we would not be competitive. So in order to actually go beyond the neutral limits, we would have to do a lot of optimization and, of course, improve on signal efficiency and so on and so forth. The other scenario that I wanted to mention then is the DUNE experiment. So it's a long baseline neutrino experiment where the interesting feature is a near detector in which there is an extremely high intensity neutrino beam. So basically, here's a detailed outline of the drawing of the near detector target hole or target area where they shoot a 60 to 120 GeV proton beam on a graphite target. And there is a decay pipe in which the hadrons from this process decay. And of course, there is so there will be, as a side effect, an enormous flux of muons that would hit this steel target. And so this would be a beam dump scenario. And because it's a long baseline experiment, they have a near detector complex very actually close, like roughly 300 meters from this steel beam dump region. So if boson would be created here, it could fly all the way out here, and maybe this muon plus minus excess could be seen in the liquid argon detector. So, of course, the question is what is the energy flux of the muons from this production? So we reached out to the DUNE beam group, who actually provided us with the full simulation of all the particles at the end of the decay pipe, and we could estimate the muon flux there to be something like 10 to the 19 muons per 1 year of operation. And the peak of the energies is very low, like a few GeVs, but it has an extremely long tail. So if you compare with the curve of the cross-section, you could see that basically this higher tail would be responsible to enhance production because the cross-section rises so steeply. Of course, in the case of DUNE, we would be in a visible mode. So we would look for a mu plus mu minus pair without any other activity. That would be the signature. Possible backgrounds could be neutrino trident production, which actually has very small cross-section. And it's actually implemented in the Gini neutrino event generator. And if one looks at this process and the mu invariant mass distribution, one finds that it's a steeply falling distribution. Another possibility that could produce mu plus mu minus pair is neutrino argon quasi-elastic resonant or DIS scattering with meson production and decay. Again, this can be simulated by the Gini even generator. If there are all these cases, you would have additional hadronic activity seen in the liquid argon. So basically discriminating for low multiplicity events and no hadronic activity, potentially also using the mu plus mu minus invariant mass cut, one could basically eliminate the backgrounds, and I basically use the Gini even generator to simulate all the processes for something like 5 years of operation and develop some truth level cuts in order to eliminate all the backgrounds, and the most important one, basically the multiplicity. Full detector simulation would be nice to be done. It's at still at the level of the truth level studies. So assuming all this that I just said is true, one can get rid of all these backgrounds. Then assuming a 10-year of operation or 20-year of operation, a decay branching ratio of 70%, thanks 5 minutes, and 5 by 5 meter liquid argon near detector, one would be able to reach a new limits overcoming the NewTEF limit, although still far away from the Muon G-2 benchmark region. And so the final thing I wanted to mention is charge lepton flavor violation could also be realized by some high energy scale BSM physics that is manifested at a low energy as an effective interaction, basically for fermion interaction, through dimensional 6 operators. And some of these possibilities were outlined in a paper from Sergey from 2018. And so the idea is that because we don't know what the new physics is, we could allow for all types of operators, scalar, vector, and tensor. And of course, there are existing limits for some of these operator. Well, some of the dimensional coupling in front, what sort of limits they could have from Zeus and from rare meson decays. But apparently, there are missing limits on tensor operators and for mu tau conversion case, and also for multiple flavor combination of initial and final state quarks. And so because Na64 is an inclusive mode experiment, we would be producing all the possible quark flavor combinations. And so that could be a way to reach unexplored territories. And the other interesting feature is that the tau in this final state of this conversion would be boosted in a very similar way because it uses the same beam. So the energy range of the final state muon from the tau decay would be also sort of in the range that Na64 could be able to trigger. So we believe that this would be also interesting to investigate. So then one of the next steps is to implement this also at the truth level, in implementing the differential cross-section, and then implementing it also in the full simulation of Na64 and determine sensitivity reach. So thanks a lot for my talk. That's all I had. And also, we are open to other new exotic ideas for muon on target tests. We have the machinery to kind of explore these possibilities. So if you have ideas, they are very welcome. Thanks a lot. Any questions?
Thank you. Questions?
Thanks, Balint. This is Mateus. I had 3 questions actually. First one is on the DUNE near detector. In your sensitivity, do you assume any backgrounds? I missed it. If you.
Yeah, so this is where I listed them. So possible backgrounds would be neutrino trident production from neutrino interaction. So maybe I just went through this slide too fast. So what you see at the bottom right is the neutrino energy distribution, and using for example, the trident production cross-section, one could calculate what would be the expected rate of events from that process. However, from my simple-minded initial exploration, this process has a very small cross-section, and especially at low neutrino energies, a few GeV, which is the case for DUNE, it would lead to a small rate of events. And in addition, the final state in the trident production, one could take the final state mu plus mu minus invariant mass as a way to discriminate this from other types of excessive ions. This is again something that would have to be simulated. The other type of backgrounds is neutrino scattering on liquid argon through quasi-elastic resonance or DIS, basically weak interactions. And if there is for example, resonant production where you create mesons that could create or DIS or even DIS, then they could also produce, in addition to the charge current interaction from the neutrino turning into a muon neutrino turning into a muon, you could also have an extra muon produced from the meson decay. However, all these processes seem to be associated with a lot of additional hadronic activity, which in the liquid argon could be seen. So if the discrimination would be to require extremely low multiplicity events, then these backgrounds
yeah, way back in the day when I was looking into Trident production, the main issue with two muons was coherent pion production. So if you have a small detector like this 5x5, mu pi events from coherent production leave no hadronic vertex, and the pion misidentified as a muon was by far the dominant rate of background. So I think that might be the limitation here.
Okay, thanks. That's a very good tip. Thanks. I will look into it.
The other question was for the operators that you had at the end, is an A64 competitive with tau decays, for instance, tau 2 E or mu pi? Because I know those have
from the paper, yeah.
Very small branching ratio constraints, right?
Yeah, so indeed, it's not competitive in those channels. So the idea of this, but as I said, what I take from this paper is that the unexplored territory in certain parameter spaces would be associated not with those channels that you mentioned, but certain other quark combinations which are not included in this modes. This is my naive understanding. So I'm not saying, or we are not saying that it's a competitive with these rare meson decay modes.
Okay, thanks. And if I may, one more. Have you considered, instead of phi decay in near detectors for neutrino experiments, instead phi scattering into mu tau pairs? Or is that just very, very suppressed?
I have to think about it. I cannot answer it right now, but I certainly haven't considered it. So thanks a lot for this idea. I will definitely think about it. Yes.
Okay, thanks. Thanks for the nice talk.
Thank you. Thanks.
So this last part with the effective operators, then one could possibly use if one of the quarks is a charm quark, then there will be no constraints from the tau because they don't decay to a charm, and the charm doesn't decay to a tau unless it's a D sub S, right? That would be I would think that would be a good physics case because it wouldn't be constrained by B factories, for example.
Thanks.
Any further questions, comments? Okay, if not, then let's thank Balint again. This is the end of this session, right? Yes. So we'll come back up, I think.
This one here, what's that? Is the possible to have later on I'm glad to hear about the. I don't know. I don't know.
Oh, really? Okay. Okay.
And they don't even consider it.
anything other than operations. I hope you ever built another.
If you capture,
Formula would be
Oh,
paralyzed.
okay.
Here, just to mention that we want to build a hydro. Yes, that's true at Fermilab
I
still.
see,
And
okay.
by it being a routine affair.
And demonstrated to be routine.
Yeah, I think you're stating that correct.
But it's not true in.
What are you getting the loop for?
Quality is
Not
not
a reality.
dangerous. Yeah, right, right.
In Fermi reality.
Ah.
The upscattering into this. And it's. So you say your power.
Very short.
It is short.
Well, you can make that scalar.
Competing with